Hey, thanks very much. Hey, I'm Dave Ditzel from Esperanto Technologies, and I'm here today to talk to you about not just RISC-V cores in PowerPoint, but actually real live RISC-V cores in systems here, and not just one or two cores, but going into the data center with thousands of RISC-V cores for AI and beyond. So what I'm going to do today is address a simple question here. If you've got a lot of computing to do and you want to do it in RISC-V, how many high-performance RISC-V processors could you actually put in some reasonable unit? Let's just say a standard computer rack, okay? It's a nice unit of volume if you're thinking about building up a data center here and want to think about how much processing you could get. Well, it helps to start with more than one core on a chip, and what Esperanto has implemented is a chip with over 1,000 RISC-V cores on a chip. And these are not little embedded 8-bit cores. These are full 64-bit RISC-V instruction set cores, along with a 512-bit vector unit on every single one of those 1,000 cores on a chip. Now, in addition to the 1,000 we call our ET minion cores, those are the ones that do a lot of the heavy weight work for integer and floating point, we also have 4 high-performance, out-of-order Maxion cores. And those are the cores you might use to, for example, boot a Linux operating system or run as control. But often in the usage of this particular chip, we're tied as an accelerator to an Intel or AMD server chip, right? And they have so much work to do, they can offload it to our chip and be more energy efficient. Now, it's not just about getting CPUs on a chip. You actually have to think about the whole system and how it works and having multiple levels of caches. And so on die, to cut down the memory traffic and reduce the power, we have this 160 megabytes of on-die SRAM. And that's for the level 2, level 3 caches, and also for Scratchpad. But that's not enough memory to run all of your apps. We also can provide up to 32 gigabytes of external memory, and we want to do that in a very power-efficient way, so that's done with LPDDR4X DRAM. That's the same kind of DRAM you probably would have in your cell phone here. A lot of other features here, but these 1,000 cores are all put on a single chip, 24 billion transistors in TSMC 7-nanometer technology. So how do we put 1,000 cores on a chip? Well, let me just talk a little bit about the structure. We've had other talks where we've given more detail about exactly how this is put together. But one of the things we realized is you need to group things in particular kinds of clusters. So we call a particular cluster of CPUs a shire of CPUs. And we put 32 of our ET minion cores in a shire, along with 4 megabytes of SRAM. So each of these minion cores, again, is a full 64-bit RISC-V CPU core. Each one of those cores has an attached vector unit that's optimized for the type of data types you'll find in machine learning, which is typically 8-bit float, 8-bit int, 16-bit float, or 32-bit float. And these are arranged in groups of 8. And that was because there's a certain amount of distance you can go with the wires in 7-nanometer before you start to impact your cycle time, right? So a lot of this design was very much considered from the technology node we were implementing in. How do you partition it? How do you balance out the memory system here? And then this particular group is connected up to a network on chip here on the far right. That's called a mesh stop here, right? And that lets you connect up to another group of 32. Now, depending on the type of app you're running, for machine learning, a lot of things are very deterministic. You don't want to take cache misses. So you choose, if you wanted, to use all of that 4 megabytes as a scratchpad, and you'll never have a cache miss. But you can also, under software control, configure that 4 megabytes of memory to be partitioned into scratchpad, a level 2 cache, which is private just to these 32 cores, or as a global L3 cache. And this is your slice of that L3 across the entire chip. Okay? Now, in order to save power, we run the power-intensive parts, so say the vector unit and the RISC-V core, we run them at a very low voltage. So what we do is design as if we were designing a 6 or 7 gigahertz processor, but instead of trying to run at that really high speed where things are inefficient, we run it at sub-gigahertz ranges, but at very, very low voltages. So this chip was designed to run kind of at a nominal voltage of about 400 millivolts. When the normal voltage you'd see off NVIDIA or somebody else would be about twice of that on a chip, okay? The dense memories, though, you have to run at a nominal voltage. That's because the fab makes those cells so tiny they can't tolerate changes in voltages. So part of our expertise is knowing, how to divide up the different voltage domains on the chip, different frequency domains, in order to balance all of these out to give good performance on your applications here. So we then take this group of 32 cores, and we stick groups of these together here in a tiled array on chip. And so we end up taking what, say in the center, might look like a 6x6 array. We take the top two pieces apart and we put our out-of-order minion cores there. We put our PCIe control logic designed for test. And that leaves us with 34 of these shires for the minions. And so you take 34 times 32 processors per minion. That gives us 1,088 ET minions on the chip. We add that to our 4 Maxions, and there's also one service processor. And so you get a total of 1,093 RISC processors on a single chip. And on the left and the right sides of the chip are the DRAM controllers where you bring a memory in and out of the chip. Okay. So here's kind of a picture of what the chip layout looks like on top. You can see the individual minion shires here. And then there's a picture of the package down at the bottom right here. There's over 30,000 bumps on the chip so that we can individually control voltages in different domains. Each one of those shires could, in theory, be on a totally independent voltage domain. That lets you account for VT variation, other issues here. And I think that maybe the most surprising thing about this design is about the power. If you look at a typical x86 core today, it might be 3 to 4 watts per core. We're only running about 10 milliwatts per core. So for 1,000 cores running, plus everything else on the chip, we can typically have the entire chip be on the order of about 20 watts. Now, that'll depend on exactly what you're running. And I'm going to show you some examples later to show you how that varies. But the point is, this is still a spectacularly low amount of power here. And we look at the external chip interfaces a little bit. This is a full system on chip. So it's got interfaces for USB, JTAG, flash ROM interfaces, PCIe interface as well. So you could run this entire system standalone if you wanted to, or, as we say, run it as an accelerator in a larger system connected to a host. So let me show you what it looks like if we put this chip on a board. So our chip is in the center here. You can see the 4 DRAM around the corners here. And the really nice thing, because this is so low power, is it doesn't take very much for a heatsink here. So just a simple aluminum heatsink. So I forgot to bring one today. We are shipping this to customers. Are there any of our customers in the audience here? There's somebody who's got a board, one of our customers. What's the name of your company? And you've got Esperanto boards in there? Okay. Awesome, thank you. Anyway, so there are real customers that are getting boards, some here at this conference, some elsewhere. And we're delighted to actually be here shipping after a couple of years of talking at this conference and saying what we were going to do. It's nice to say, hey, we've actually done it. We're actually shipping parts to customers today. So how would a customer typically use this card? What could you do with it here? Well, here's a system that we recommend here. It's a standard 2U high server, and it can take up to 16 PCIe cards, right? And I'll leave the details on here if you want to look at the slides later. As soon as I figure out how to get the slides uploaded, I'm having a few issues with the website. But the way this works in a system, in order to get 16 cards and very high bandwidth, there are actually 2 Intel Xeon CPUs in this particular server. There's a corresponding server with AMD CPUs in it. But this lets us plug each one of our cards into one of the backplanes and have a very high bandwidth interface to those Xeon CPUs that are coupled with a UPI interface, so they appear to the system as one CPU. So no matter which CPU you're talking to from the host, you can get to all the PCI and have very good bandwidth here. So in one server then, with 16 cards, we can put 17,500 RISC-V CPUs. That's a lot of computing performance here. So if we go further, how many can you put in a rack? Well, A standard rack is maybe what they call 42 U high. A U is 1 3/4 inches here, right? So there's room for about 20 servers and still a little bit of space left over for a top of rack switch here, right? So we could put 320 of our PCIe cards in here. So that amounts to just about 350,000 RISC-V processors in a rack. So that's a lot of performance. And while we do floating point, we do a little bit higher performance in integer. So in int8 here, that's about 26,000 teraops per rack of machine learning performance that we can apply. So again, very high performance with RISC-V and in the data center. I've heard other companies earlier today talking about going into the data center. Well, here's an example of a part that's actually not being promised, but actually shipping today. We have a software stack that makes it fairly easy to use RISC-V. Now, for machine learning, most people will program with a machine learning framework, like PyTorch, or you can also come in from TensorFlow or something, any other of the interfaces through what's called an ONNX interface. It's the Open Neural Network Exchange. So you compile to that. We read in that format then we automatically parallelize across the 1,000 cores and then vectorize on each one of those cores to solve the particular machine learning problem that you're doing. And then it spits an answer back to the host CPU. And this particular system will also divide up the work amongst several different chips. So, what's it like really running here? We've had a lot of people say, I don't believe your power numbers. How can you possibly be that low? So here's some real power numbers here. So power comes in a lot of forms. One is the power of the chip, but the other is typically the customer is more interested in what's the power of the card. So that's got to include all the DRAM, the flash memory, and actually there's a fair amount of inefficiency from the power supplies. Just to supply, I think we've got like 12 different power supplies on the board for all little things we want to adjust to get the best adjustment there. So there's a little bit of power supply loss. And so you can see the power, for example, that the RISC-V cores take here in blue. And just as one example I've shown off to the right, if you're running the deep learning recommendation model from ML Commons, and you run the 32-bit floating point version of that, and one of the phases is called the RMC3 model there, the RISC-V CPUs are taking just a little less than 12 watts. But the board on a whole will take 32 watts. And we have broken out also the bigger two other uses of power are the SRAM on the chip, because you're always beating on that SRAM. You're calculating results, but you have to fetch them from the SRAM and store them back into the SRAM every cycle. And then also the network on chip to have things communicate. Okay. So again, the power will vary by benchmarks. And somebody said, well, how much power does your chip take? The answer is always, well, it depends. What are you doing? When it's idle, you've got one particular number. And as you run more compute-intensive things, it'll go up. But typically, at this speed, and these particular chips are optimized for good performance per watt. So they're running about 600 megahertz here. But almost always the card is under about 40 watts here. And the PCIe card limit is typically about 75. So we're about half the power of what a typical PCIe card would have here. We can go faster, we can go slower. Sort of depends on what the customer needs and what you're trying to do for the balance of power in the entire system. So just a little bit more detail when you're measuring power here. Even when we say, oh, well, the RISC-V processors, take a certain amount of power here, that will also vary while the benchmark is running. And so we have a number of tools where you can kind of monitor what's going on each one of the power supplies here. And so you can see at the top, I put down for the 3 different phases of the deep learning recommendation model. This is 16-bit floating point in this particular case, and these are the 3 typical models, RMC 1, 2, and 3 here. And you can see they each take kind of a different amount of power on average when they're running, and they're little spikes. And trust me, if you could actually put your scope on a wire inside the chip, you'd actually see many more spikes than you see putting the probe on the outside of the chip from what the power supply gets to see. A lot of that is filtered out. But it does give you a very good feel of where the power is going on the chip. So the power is going kind of mostly where we want it, which is in the vector units of the RISC-V processors. And then the SRAM kind of takes the next amount, and then the on-chip NOC. So if we found that we were being performance bound by the NOC to NOC interface, we could raise the frequency of that interface. That would raise the power up. And so you've got a multi-variable optimization problem here. For the particular problem you're working on, how do you want to optimize it? So there's a lot of knobs to turn in terms of getting the best performance out of your particular system here. Okay? So how does it perform compared to other things out there? Well, typically, the benchmark that's always quoted by everybody is ResNet 50. That's about the only thing you've got out here. I call it's the dry stone of the machine learning age, right? And so here we compare against an Intel CPU, and the Intel CPU here is the value that they report off the MLPerf website. And Intel gets a number running on 2 Sapphire Rapid CPUs of a score of 16,000. But each one of those CPUs has a TDP power of 350 watts, right? So they do 23 inferences per second per watt. Now, if you look at the NVIDIA A100 card, which is one of NVIDIA's best cards for machine learning, they do substantially better than the CPU. This is why GPUs are getting a lot of the machine learning business here, right? And you'll see they're up to 132 inferences per second per watt. But still, you've got to deal with a 300-watt card. You have no choice but to take that one increment. And so what Esperanto has done is to say, look, we'll build somewhat smaller chips, and you can put in more or fewer chips along the way here. But each one of our cards gets about 158 inferences per second per watt. So we're able to beat the GPU, but with a general purpose CPU. You weren't supposed to be able to do that, right? Everybody said, hey, Intel shows general purpose CPUs take more power than GPUs. No, it's what instruction sets you're running. So this shows that the simplicity of RISC-V helps us to achieve lower power, but retain all the benefits of general purpose programming here. So what does this let you do then? Well, if you take a look at the performance of the NVIDIA A100 or Intel's 2 CPUs, if you're a customer and you have a particular need, you can choose the amount of performance you want by putting in the correct number of cards in the system and the correct cost for where that is going. And so you really have a lot more options with the Esperanto system, and so we think we bring the customers a lot of flexibility for getting what they're looking for to solve their particular problem. So just summarizing here, I think we built something pretty incredible. We think it's the world's highest performance RISC-V chip. We have over 1,000 RISC-V cores on a single chip. We can put 17,500 cores just in a simple little server that anybody could have almost in their dorm room. In a computer rack, 350,000 servers here. We get excellent performance per watt with RISC-V, rivaling the best GPUs that are out here, but we've retained all the benefits of simple RISC-V programming. And this machine can be programmed either with our machine learning software stack, or we have a native SDK, so if you want to program down at the RISC-V level, we'll let you go for it here. And we are shipping to customers now. We're delighted to say that. And if you've got a RISC-V problem that's appropriate and you'd like to use thousands of cores, send us an email, let us know. We'd be happy to sell you a system. So thanks very much.
Excellent. 2 questions, and I'm going to be lazy and go right here for the first one.
Hey, Dave. So far, it's a unique architecture with 1,000 cores running RISC-V. What workloads have you seen that are most amenable to your architecture?
Well, certainly it's things that run in parallel. And today we're mainly focused on machine learning workloads. For example, we've had some cases where somebody wanted to do some pre-processing of an AI code, like running an FFT. So it's things that have lots of data to work on in parallel. But other than that, it's not terribly restrictive. A lot of the codes people run are basically matrix multiplies. It's a lot of multiply adds. So anything where you have a ton of multiply adds to do, and your data types match the data types that we accelerate the most, and that would be int8, FP16, and FP32, almost anything there that you really take the time to program should run pretty well on this machine.
All right, next question here.
Thank you. Yeah, thanks for the talk. I guess my question is a little bit related to the previous one. So I'm interested in how much you are limited by your memory, or whether you are limited by your memory I/O, or generally by your I/O. I imagine 1,000 cores, full-blown cores on one chip, can generate a lot of data processing. While
Yeah, the question is how much we're bound by the memory. And it's a good question. The question is, how do you know if you're doing well or not in relative comparison? And one of the answers I would say is if we look at what your ratio is, what's your sustained throughput rate versus your peak rate, right? And on NVIDIA CPUs, they tend to do maybe 45 to maybe 50% or so. We've seen in cases like ResNet 50, we do maybe over 55% efficiency. So we think we're doing pretty well, but it is very app dependent, right? It's just to really be honest. So what we've tried to do is to put a lot of memory on chip, and that reduces how far you have to go to get to memory. It's in a hierarchical fashion, so if you get to this something very often, like we've learned in computing over the last 40 years, a hierarchy of caches tends to work pretty well, and that does pretty well. And we have a reasonable amount of memory bandwidth to the outside. We've got 130 gigabytes per second across a fairly wide DRAM interface. So we went very wide, 256 bits wide, but with low cost memory. We think that's a nice solution for what we've got. And for most apps, it's a pretty reasonable balance. In other words, we don't feel like we're horribly memory starved in most situations.
So questions regarding your slide comparing between the NVIDIA GPU and your device. So I guess that it is based on the performance per watts. But if you want to have the same performance of the PCI Express card as an A100, for example, do you think you just need to have more cores available packed into your PCI card to get to the same level of performance for the A100 from NVIDIA?
Yeah, on things like ResNet 50, the PCIe bus bandwidth does not really affect things all that much because you've offloaded most of the problem to the card and it runs for long enough on the card without a lot of PCIe bus traffic. So I don't think that matters a whole lot. However, what I would say is by dividing up the problem, let's say, suppose we divided across 16 cards that we put in that system. We would have 16 times more PCIe bandwidth than the one NVIDIA card would have because it only has one PCIe slot it has to talk through. So there could certainly be advantages in breaking things up into smaller increments and using multiple cards. It really is going to vary workload dependent, though.
All right, we're going to take the last question right here, and then we'll let you all get to the end of the day. So here we go, last question.
Okay, thanks. You may have already answered it. I was also picking up on the PCIe. I mean, Gen 4x8, I think you had on each device?
Correct.
Seems like a very small amount of I/O bandwidth for that amount of compute, particularly if you compare it with the Sapphire Rapids or...
Yeah, what really matters, and what we were told by one of our earliest customers, is, look, the PCIe bandwidth won't matter. What matters is the bandwidth out to main memory. And so that's why we put 32 gigabytes on the card. So what we do is we load up the card once. Suppose you want to say, you have a picture and say, is this one of your friends, right? You have 100,000 photos preloaded on the card. You send the one photo over the PCIe bus to each of 1,000 different cards in your system and say, who's got this photo in their repertoire of their library, right? And so you're really not sending a lot of that over the PCIe bus in most cases. What matters is the bandwidth to main memory, and as long as the bandwidth to main memory to our chip is much greater than the PCIe bandwidth, then we're fine running things out of our main memory. Okay, thanks everybody very much. I'll hang around. If there's any other questions, I'll hang around by the side here. Thank you.
Let's give him a final round of applause. Thank you, Dave.